very pleased tonight to have Dr. Justin Dressel here, and he's an assistant professor of physics at the Schmid College of Science and Technology at Chapman University, so he's a colleague of mine. I'm very pleased to have him here. He's also a member of the Institute for Quantum Studies, which is a major institute that has among its members multiple Nobel laureates, National Medal of Science winners, and does some great work. His PhD in quantum physics is from the University of Rochester, and he has multiple research interests in quantum foundations, quantum information related to quantum computing, quantum field theory, mathematical physics, and computer science. Very accomplished young scientist who, amazingly enough, in addition to all this theoretical information, knows quite a bit about the business of quantum computing, and we hope to hear some of that in his talk this evening. So, without further ado, Dr. Justin Dressel.
So thank you, Michael, and especially thanks to Dan and everybody else for inviting me, and it's a pleasure to be here. Let me pull up my slides here. So since there are 3 screens, I'm going to try to use the actual mouse cursor as my pointer here, so apologies if that's weird, but I'm going to do it anyway. So I'm Professor Dressel, as Michael just said. I'm at Chapman. Chapman's a wonderful place if you have not visited.
Speak up.
Can I speak up? Is that better?
Yes.
Perfect. Okay, so I'm at Chapman. It's a wonderful place. If you've never been, I encourage you to come to Chapman and see the campus. We have a brand new science building, which is going to come online June 1st, I believe. We're moving into it very soon. In the fall semester, we'll be in the new building, Schmid College, Science and Technology, the Keck Center for Science and Technology. So I study quantum mechanics. I'm part of the Institute for Quantum Studies at Chapman. And in particular, I'm heavily involved in the pursuit for quantum computing, quantum computers. And how many people in this room have heard of quantum computing? Everybody. How many people in this room understand what quantum computing is? A much smaller subset. So, out of curiosity, I did a Google search and said, what is quantum computing? And this is the image that came up, which I really liked because it tells me absolutely everything I need to know about quantum computing in one image. You can see clearly it's mystical, just like quantum mechanics, has something to do with people and chips and squid wires and so, but this doesn't tell us much. So actually, what is quantum computer? What is quantum computing? I'll assume that most people in this room actually have very little understanding of this, so I'm going to walk through everything in a little bit of detail just to give you a better flavor of what actually is this subject and what is it doing for us that's new, that isn't already in classical computing. So what you're looking at right here is one of the state-of-the-art quantum computers that actually exists and you can run. And in fact, you can go on the web and log into a computer much like this one and run it from the cloud right now. IBM has this service. It's called the IBM Quantum Experience. If you just Google that, you'll be able to find it, create an account, and use a quantum computer right now. So technology is here. The question is, what do we do with it? Okay, so what is quantum computing? Well, the main idea, which I want to drive home here, is that computation is physics. And this is why myself, who's a physicist by training, has something to say about computation. Otherwise, you'd say, well, why am I qualified to talk about this? Well, the idea is that computation is actually physics. And classical computation, as most people who have a computer science degree know, is built around this idea of a Turing machine. And this sort of gives away the whole idea. That it's a machine. It's a physical machine. And you're describing the actions of a physical machine. And all classical computation reduces to the operation of this Turing machine. And this is such a foundation of classical computing that we even have the phrase Turing complete, and say that if something is Turing complete, it can perform any classical computation. That's just saying that what we're describing is a classical machine. And a classical machine obeys classical physics. And so everything that classical computation is based upon is constrained by what classical physics allows to happen. And this was not really realized until about the mid-60s and 70s, when people started thinking a bit more deeply about this and saying, well, wait a minute. We know now that the world obeys quantum mechanics more fundamentally than classical mechanics. Classical mechanics is sort of an approximation. Classical physics is an approximation to the way the world actually works. And as you start building machines that get closer and closer and closer to the molecular level, the atomic level, then we expect classical physics to not be adequate, not be sufficient to describe the way these actual machines work. And so this gave us a big question is, does computation need to change? If we get down to the atomic scale where quantum physics actually matters, does the whole idea of computation persist, or do we have to modify it? And the surprise that people found was that it does change. We do have to modify the basic building blocks of how we understand what computation is in order to modify it to work at this quantum scale. So the question is how? What has to change? Well, let me remind you a little bit how a classical computer works. Classical computers built out of bits of information that are either 0 or 1. These are states of some physical system. It's either this or it's that. Typically inside a computer, a bit is stored as an electrical signal, which is either a low voltage or a high voltage traveling down some wire. And again, classical physics describes the traveling voltage down this wire implicitly. We usually don't think about it, but that's what's happening. Now, if we're storing bits, like storing on a hard drive, the bits are stored as spin configurations in arrays of atoms, little magnetic domains that we manipulate. And again, we treat these spin domains as classical objects. It's either flipped down or flipped up. Those are our bits. But these are definite physical configurations, a 0 or 1. And that definiteness only exists in classical physics. When we go into quantum physics, we have to sort of expand upon this idea a little bit. So in one slide, these are the main new things that we have to consider when we bring about quantum physics. Well, there are 4 new things, and we call them all collectively coherent features of physical systems. The first thing is a superposition. This is a brand new concept that comes out of quantum physics that says not only are 0 and 1, for example, the only definite states that there can be, but anytime I have a system where I have at least 2 possible definite states, like 0 and 1, then quantum physics tells us that actually we have many, many more possible definite states, somewhere in between 0 and 1. And I want to emphasize this point because most people get it wrong. Most people say, oh, it's like 0 and 1 at the same time. Well, that's a little bit too vague. A better way to think about it is it's somewhere else entirely. It's somewhere in between 0 and 1. And we can tune where it is in between over an entire continuous range. So, in fact, we have an infinite number of other possibilities that are all definite. And this is really shocking, and it's one of the biggest surprises going to the quantum realm, that we started with something where there's only 2 possibilities. It's discrete. 1, 2, and that's it. And by adding quantum physics, suddenly we get an infinity of other possibilities that are equally as valid and equally as definite as 0 and 1. Now, if you're familiar with how light works, you might have an intuition about this, which is if I have a laser beam, this laser beam has a property called polarization. This polarization means that my light can be sort of waving this way as it travels as a wave, or it can be waving this way, which we call vertical polarization and horizontal polarization. And in some sense, those act like bit states. Vertical polarization can be a 1, for example. Horizontal polarization can be a 0. They're perfectly distinguishable, and I can treat them as bit states of 0 and 1. But the point is that with such a light wave, I can rotate the beam in 3D space. And I can get not just up and horizontal, I can get any angle in between. I can get a light definitely waving at this diagonal. It's not that it's it's not vertical and horizontal at the same time in some sense. It's actually definitely diagonal. It's this completely new direction. But if I pass it through what's called a polarizer, which is something that picks out only vertical or only horizontal light, then I will see that this beam will get through only a fraction of the time. And when it gets through, it will have changed. It will have changed to become whatever I passed it through. And this is the kind of intuition you need to understand what's going on here with a quantum bit. Is that what you actually have are definite new states, like these diagonal directions, which are perfectly definite, but they're different from what you had before. And we can pick out any range of these definite new states we want. And when we do that, what we find is that we actually get a sphere of possibilities. If we look at the geometry of how many definite states do we have, and where do they exist, and how can I get from one definite state to another, they map out a continuous set of points. Instead of just 2 points, I have a continuous set. And that continuous set is all over the surface of a sphere, just like this sphere I have here. And what you see is that the points 0 and 1 are just two antipodal points on the sphere. Those are our bit states we started with. And every one of the other points on the surface of the sphere is new and given by quantum physics. It does not exist classically. And to complete my analogy with the beam of light, if I'm rotating a beam of light so I get some diagonals, this would be like going over a great circle on this sphere. So every point on this represents some diagonal that the bit state can be. Okay, so that's the first feature that's new. And this is a highly non-trivial feature, that we get an infinite number of states of bits. We can never have just 2. The second we introduce just 2, we get this entire sphere that comes along for the ride, no matter what we try to do with it. So we have to cope with this sphere. We can't get rid of it. Okay, the next thing that happens is entanglement, which I think most people in the room probably have heard the word entanglement, but probably don't have a deep understanding of what this means. In some sense, entanglement is just like classical correlation. It's saying that if something over here happens, then something over there is likely to happen as well. And they may be correlated with each other. But quantum entanglement sort of goes a little bit beyond classical correlation, because it can be correlated in ways that cannot even exist classically. Just like I can be in bit states that can't even exist classically. And so the intuition about entanglement sort of breaks down a little bit if you try to think about it solely as correlation. The better way to think about it is that what actually happens is that when you have 2 bits, for example, then the space of the possibilities of what those 2 bits can be grows. And it grows exponentially. So rather than just having a sphere for bit 1 and a sphere for bit 2, in fact we have 4 possible angles that we can go across along some continuous manifold that goes all over some larger space in these 2 spheres. And everywhere in that continuous space is a definite 2-bit state. And those definite 2-bit states can be completely different than saying each of these bits is definite independently. There can be a definite 2-bit state that is a correlated state such that each of the individual bits are indefinite. And this is something that has no analog classically and takes a long time for your brain to get some intuition about. It's completely new. But there's a very simple phrase that I like that sort of encapsulates what entanglement actually means, and that is more is different. It breaks modularity. And this should make you a little bit uncomfortable as a computing audience, because everything about computers you sort of assume is modular. I can build something out of smaller pieces. If I understand what all those smaller pieces do, then I understand the whole. What actually happens is if I have individual pieces, I can understand all of them very well. But when I put them together, I get something entirely new that has a lot more room in it than each of the little pieces started with. And that extra room, as we'll see, is what will give quantum computers the capabilities of going beyond classical computation. So we actually want this entanglement. We want this extra room in order to go beyond what we can do with classical computer, but it takes a while to wrap our brains around that. Okay, and what we'll find is that if we get n qubits, then we're going to need 2 to the n continuous parameters to describe all the definite states that we can get with n qubits, which means that the number of continuous parameters scales exponentially instead of linearly. And that exponential scaling, we'll see, will be a theme in quantum computation. The third thing that's new is time symmetry. In a classical computer, we're used to thinking of AND and OR gates, for example. Well, an AND gate, if you think about what it does, is it takes 2 bits and it outputs 1 bit. And so you can ask, can I have an inverse for an AND gate? Well, you can't, because the number of bits changes. I'm going from 2 to 1, I can't go backwards. Well, it turns out that in quantum mechanics, everything's time symmetric, just by nature, which means that if I have an evolution that takes me from here to here, I can equally well have an evolution that takes me backwards there to there. Which means I need to think fundamentally time symmetrically if I'm going to understand how things work. And to give you a little bit more intuition on this sphere, if I start with a definite bit state, that is this orange dot, then I can say apply some operation on my quantum bit, and this definite bit state can follow some orbit along the surface of this sphere, usually some circular orbit, like so. But any such path on the surface of the sphere is reversible. I can just travel the path backwards. And that gives you an idea of how to think about operations that you do on this bit. It's really taking a point, moving it around this continuous space, and I can always move it backwards. And this is true even if I have 2 to the n parameters. I can still just continuously move things from here to there and continuously move them back. So that'll change a lot about our intuition about classical computing immediately. The fourth thing I alluded to a second ago, which is that if I look at a bit state, then I will occasionally get an answer and occasionally get a different answer. So there's an intrinsic randomness that happens in quantum mechanics, and people know about this randomness as quantum state collapse. You hear that word a lot. And when I was talking about the light wave, I alluded to this, where if I have a definite diagonal light wave, for example, and I pass it through, say, a vertical polarizer, then what you'll find at the level of an individual particle of the light wave is that some of the time it'll get through the polarizer and come out the other side. And when it does that, it will have become a vertical light wave instead of what it was before. But some of the time it will not make it through that polarizer, and it'll just be blocked. And whether it makes it through or not is completely random, as far as we can tell. There's no way to predict which one's going to happen. So there's this irreducible probabilistic nature when you measure a quantum system. And that will have non-trivial consequences for trying to understand what computation is like in such a system. We say that the qubit, for example, will randomly collapse to 0 or 1 when we look at it at the end of the computation. It's a little bit funny, but that's how the world seems to behave, so we have to deal with it. Okay, so let me go a little bit more detail here at the risk of putting math on the board, because I want to make one more thing clear, is that quantum bits are much, much closer to something called a probabilistic classical bit than a definite 0 or 1. So if you can understand what a probabilistic bit does, then you'll get a little bit more intuition about how a quantum bit behaves. Now what a probabilistic bit is something that can occupy an uncertain state. So we don't know for certain whether it's 0 or 1, but it's somewhere in between. We have some probability of it being 0, probability of being 1. And in such a case, we can always define some continuous parameter, like z, which on this graph will be this vertical black line, as the difference between the probabilities of bit state 1 and 0. So probability of 1 minus probability of 0 will be this coordinate z. And so what this means is that I have, say, this blue diamond that can slide up and down this line here, and anywhere along this line is a valid state for this probabilistic bit. And we see that that forms a continuum of possible states. They're all probabilistic. Now this should sound familiar. It's similar to what I just said. Rather than two states, I now have an infinite number that are continuously connected. But they're going sort of vertically up and down, connecting these 2 points. Now, what happens when you go to a quantum bit is that we preserve that structure. That's still there, probabilistically. But it's there as the axis that connects the antipodal points. So if I pick a 0 and a 1, like 0 on the bottom here, 1 on the top, then I can still define this probabilistic coordinate, which is this vertical axis here. And I can drag my state up and down the vertical axis, and that would be an uncertain bit state. I have some probability of it being 1, some probability of being 0, but it's not definite. Which means, if you look geometrically, I'm inside the sphere. And that's the general rule, is that anytime I'm inside this sphere that corresponds to a quantum bit, I have an uncertain state. It's not definite. However, if I'm on the surface of the sphere, then it's just like being in this bit state 0 or bit state 1. I'm definitely in that state, whatever it is. And so what you're seeing here is that I can take the idea of a classical probabilistic bit, and all I need to do to get the quantum bit is rotate this around so that I map out an entire sphere. I take this one axis, which is my probabilistic classical bit, and just rotate it around, get a whole sphere, and now I have a quantum bit. And that should help build your intuition about what we're talking about. And this also emphasizes the point that this is fundamentally new. It's not just a probabilistic bit. It's an entire sphere of possibilities of rotating a probabilistic bit around. Okay, but everything that you do with a probabilistic bit has an analog in a quantum bit. There's just more options. There's more room, again. Okay, enough math for now. Let's go back to computation and say, okay, I've introduced to you how a bit changes. Now, what happens to the rest of classical computation? Well, the first thing we have to do is figure out what is the analog of classical computation that I have to think about in order to generalize it to quantum physics. And what I said earlier about reversibility is the key. That I need to start from a reversible logic model for classical computation. And then I'll have a hope of generalizing it to a quantum model. So that's what we'll do. So we'll start with reversible classical computation, and then say that quantum computation should decohere to this model when those coherent features wash out. And then we'll get a probabilistic version of this reversible classical model as a result, when quantum physics washes out and we go back to the classical physics domain. Well, that means we have to go back to redefining our gate set into something that's actually reversible. So AND and OR and NAND gates that we're used to, those won't work. Just throw them out. Instead, we have to go back to reversible logic gates. And reversible logic gates have been around for a long time in the classical world. Here are three main examples. The NOT gate is reversible. I can just flip a bit. I can flip it back. It's no problem. Controlled NOT, C NOT, is also reversible. I can flip a bit based on what the state of another bit is. If this bit's 1, I flip that bit. If it's 0, I do nothing. And of course, I can invert that. And I can introduce two control bits and have a controlled NOT, which is also known as a Toffoli gate. And just like the controlled NOT, this is reversible. Now what's nice is that this Toffoli gate is a universal gate for classical computation. With this one gate, this Toffoli gate, just like with a NAND gate, you can get everything, all of classical computation from this one gate. Which means if I can understand this one gate well, and I can generalize it to quantum mechanics, then I'll be able to understand what we mean by quantum computation. Now, to point out why this is universal, if I fix one of these bits here to be a 1, then I'll get a controlled NOT out of it. So this reduces to controlled NOT. If I fix this bit in the controlled NOT to 1, then I'll get a NOT. So these two gates are actually a subset of the Toffoli gate. It turns out any other gate I want, I can make out of Toffoli gates. So the idea here is now we have a very solid prescription. I understand the theory of computation extremely well from the point of view of reversible Toffoli gates. And all I'm going to do is upgrade the bits that appear in this gate to qubits. I'm going to make them quantum. And everything else stays exactly the same as in classical computation. And that gives us a very clear prescription to understand what changes, what's new in this new theory of computation that did not exist prior. Because I know exactly how it reduces to a classical theory I do understand. Well, here's what happens when we do this. We get three main new features. The first is what most people hear when you hear quantum computation and everyone says, oh, what's the big new thing that you can do that you can't do before? This word parallelism comes up a lot, quantum parallelism. So to be a little more specific about what's going on here, we can get superpositions of these bit states, like 0 and 1. The superposition is just some combination of those things. It's like rotating it to some other definite state that's in between somewhere. And it turns out that when you perform an operation on those bits, like here x is a bit flip, then it just linearly goes through the whole superposition. Which means that if I have a superposition of every possible state of my bits, which is possible, I can do that, and I perform an operation on that, it's going to perform an operation on every possible state of my bits at the same time. And I'm going to get some new superposition that contains all of the outputs of every possible input. And that's what people mean by quantum parallelism. You're effectively parallelizing over every possible input in one shot. I pass one state through my gate, and out on the other side, I get all the possible answers for that gate in a superposition. But there's a caveat. That's a superposition. And that means that when I try to look at it, I'm going to face this quantum randomness that I mentioned. I look at it, it collapses. And when it collapses, it randomly chooses an output. And so if you think about that, I can have exponentially many things performed in parallel. But when I try to look at all of them, I'll get one result randomly. And I'm going to have to repeat that exponentially many times in order to sample all of the possible outputs. So in fact, I sort of get a wash. I get all this parallelism, but then when I try to look at it, I still have to repeat it exponentially many times. And in fact, it's worse because I'm not guaranteed to get every output sequentially. I'm going to get repetitions in there, and I'm going to have to repeat it probably more than the number of all the possibilities in order to properly sample everything. So it seems like just from that, I haven't done any better. I've introduced parallelism and then I've killed it. But it turns out that there is one more feature that saves us and really allows for something fundamentally new. And that's because there are new gates to convert a definite bit state into another definite bit state, which is a superposition, then I can get new features in those superpositions that I wouldn't be able to have with a probabilistic bit. Those new features are these minus signs when I do a superposition. And what this minus sign will allow us to do is cancel out a positive sign somewhere else. And so what this means is I can create a superposition and interfere it with a different superposition of a bit state. And what will happen is I'll cancel out one of the possibilities that I would have to measure. And if I can do this enough times, just cancel out exponentially many of these possibilities, then I can get down to a small set of outputs that I will measure with very high probability. And so the idea then is that if you can do a parallelized computation over a big superposition of inputs, and then do something that uses this interference to cancel out most of the outputs that I don't want to look at and preserve only some small set, then I can preserve the parallelism. I can preserve that exponential speed up and still be able to sample only a few things randomly and get the answer I want. And that's the magic sauce. So parallelize, interfere destructively, so cancel out most of the outputs, and then randomly sample a much smaller set. So At this stage, now that I've introduced kind of the background here, we can ask the key question that everyone's interested in. Is a quantum computer more powerful than a classical computer? Well, it turns out that the answer to this is technically unknown, but that's because we cannot prove that any of our classical algorithms are the optimal ones. So what we can say is that based on all the classical algorithms we know, which we believe to be optimal, or believe to be the best we can do, then quantum computers are more powerful than those algorithms. And so there are strong indications to believe that that's a general result, that quantum computers really are more powerful. But we actually have no proof that this is the case. It could be that some very, very clever person will come up with an even better classical algorithm which will match a quantum computer. It's unlikely that will happen, but it's not ruled out. But the rough logic of why it's likely that it is more powerful follows these three things that I just said. You can parallelize computations over superpositions, which can exponentially speed up a single computation. Because I have exponentially many possible states that I can be in a superposition, then if I can do in one shot an operation that just linearly composes all of those exponential possibilities, then in one shot I've exponentially accelerated my computation. With the caveat that randomness kills that, unless I can do some destructive interference, kill all of my outputs, and get back only a few, a subset of a few. And this is hard. To get all these three things right in order to get an algorithm that is truly better than a classical algorithm is hard. There are only a few cases where we know where this really works well. And there's sort of an open table for talented new young programmers to come in and find new clever ways of using these three things to accelerate computations. But I'll give you an idea of how this works for something that we do understand quite well, which is the Fourier transform. Now, it's taught, I believe, in most computer science classes that Fourier transform, when you do a discrete Fourier transform, then you have doubly exponential number of operations you need to do. It's basically a giant matrix multiplication. You end up with 2 to the n times 2 to the n number of multiplications and additions that you need to do classically. And this is extremely slow, but the Fourier transform is so useful that people found a way to short circuit this computation with only some minor degradation in fidelity. And this is called the fast Fourier transform. And effectively, it's just a clever recombining of terms to short circuit this exponential in order to get rid of one of these exponentials in the runtime and make it linear. So I reduce one exponential to linear, and we get the fast Fourier transform. And that is used all over the place in most of science, most of engineering, all of signal processing. It's used everywhere. Fast Fourier transform is one of the most used algorithms that I know. Well, it turns out that if you have a quantum computer, you can do even better than that. You can take this extra exponential that's remaining in the fast Fourier transform and make that linear as well. And so you get something that scales quadratically in the number of bits. And what that means is that effectively you're doing the whole matrix multiplication in one shot. And this is exactly what I was saying. You're getting an exponential improvement in one shot. So the way it works roughly is illustrated here, that if I set up a particular superposition, like here I have a superposition of all 2 to the 3 states here, 0, 0, 0, all the way through 1, 1, 1, and they have phases in front of them that are periodic. So in fact, what I've done is I've encoded information in the phases out in front of all these things, in factors of e to the 2 pi I over 8. And so I just walk through all these phases periodically as I go from here to here. And I set up the superposition, and now I can think of it as kind of a periodic signal that's encoded into a single triple bit state. And what the quantum Fourier transform does is, after going through these reversible gates, this is called the Hadamard gate that sets up a superposition. This is a controlled rotation, another controlled rotation around each of these bit spheres, another Hadamard to flip superposition, another controlled rotation, another Hadamard. After this sequence, it performs a Fourier transform. And so what you see is that this superposition here comes out of each of these gates and gets progressively closer and closer and closer to a single element. And coming out here at the very end, you'll see that there's a definite single state. And in fact, what happens here is after this Fourier transform, I get the definite bit state 0, 1, 0. And what this is telling me is that I have a periodic signal with periodicity of this phase factor squared, which is what this 0, 1, 0 means. It's 2 in binary. And so I've converted something that's a periodic signal directly to its frequency content in one shot in a linear number of gates, linear in the number of qubits here, or I guess quadratic in the number of qubits here. And that's fantastic, because if we can do that and we can use it, then everywhere the fast Fourier transform is useful, we would expect this quantum Fourier transform to be equally useful. But of course, there's the big caveat, is that the output is generally a superposition. Generally, if I have an arbitrary signal and I take its Fourier transform, I don't get a single spike. I don't get a single frequency. I get a whole range of frequencies. And so I just go from one big superposition to another big superposition. And if I try to sample that by measuring it afterward, then I will have to sample exponentially many frequencies in order to figure out what they are. I get no benefit. But if I have a problem where I know that the frequencies at the output are sparse, where I can get 1 frequency, 2 frequencies, 10 frequencies instead of 100,000, then I get a huge advantage, because when I sample, I'm guaranteed to get one of those few sparse frequencies. And that's the catch. So if I set up a problem where I know the periodic output should be sparse, then I will get a dramatic advantage from this quantum Fourier transform. And the best known example of where this is useful is called Shor's algorithm. Shor's algorithm is an algorithm for factoring large integers. And the way this works, very broadly speaking, is that you convert this factorization problem, just with number theory, just classical number theory, into a period finding problem, where you just take successive powers of something and you find the periodicity of when it comes back to itself modulo something. And by converting the factoring problem to a period finding problem, I can now use the quantum Fourier transform. And the benefit of this is that by the construction of the problem, I know that there are going to be a sparse set of particular frequencies in the problem. And so when I do the Fourier transform, I know I'm going to get a sparse set of frequencies on the output. And then if I sample the sparse set, I can do that sampling efficiently. And then that preserves the exponential speed up of the Fourier transform. And here's a graph of what that actually means. So if I take the number of digits in my bit string that I'm trying to factor, here it's going up to 300, then the best classical algorithm for factoring this very large integer is called the number field sieve. And that scales as the exponential of the number of digits to the 1/3 power, roughly speaking, which is this red curve here. And if you can see on the left here, the number of operations that you have to do very rapidly increases. So by about 200 bits, I'm talking about 10 to the 26, 10 to the 27 operations, which is a lot. In fact, the current record for being able to factor such a number on a classical computer is only 230 digits. And they sort of saturated because that's way too many operations for a classical computer to do. They just ran out of computing time, effectively. But if I were able to do that on a quantum computer and do this algorithm with the Fourier transform, then I get this blue curve. And by this 230, which scales as roughly d cubed, the number of digits cubed, so by this 230 digits, I'm still in the realm of 10 to the 6th or 10 to the 7th operations, which is doable. And what this means is I'm able to factor a large integer in reasonable amount of time if I can do it on a quantum computer. And the reason this has gotten people so excited is because this whole idea about factoring integers being difficult is the basis for most encryption schemes. Most public key encryption schemes like RSA function only because factoring integers is difficult. If factoring integers were easy, nothing would be secure in these schemes. And so this gets people excited. If we suddenly break all of people's encryption, that causes some problems. And if you aren't familiar with RSA, this is the same encryption scheme that's used every time you go on Amazon, use your credit card, and it's stored in the cloud, and you send your digits. It's using RSA encryption to send it back and forth in order for your information not to be just freely available on the web. And so if you can crack this, then everybody's credit card suddenly becomes fair game. And more importantly, RSA encryption and other similar things are used to encrypt data as well. And so you can imagine if a government agency tried to hack into another country's web server and decrypt all of their sensitive files, people might get excited. So this one algorithm is driving a huge amount of interest into quantum computing.
Also banking. All banking uses that encryption.
All banking uses the encryption as well, yeah, so it's significant. So this brings us to sort of the million-dollar question, right, or maybe billion-dollar question. How close are we to having a computer that can do this kind of stuff, to a practical quantum computer? And what I'll point out shortly is that we already have them. We already have quantum computers, sort of. And this sort of is the key asterisk when I'll explain what I mean by that. But there are two main computing technologies that already exist. One of them is called trapped ion technology. And I'll explain what that means. The University of Maryland recently demonstrated a trapped ion computer that has 53 quantum bits. And again, remember that the amount of information I can store in this scales is the exponential of that. So think about 2 to the 53 possible bits. That's actually what I'm talking about with 53 qubits. The second competing implementation is superconducting circuitry, which I'll talk a little bit about. And the current record is held by Google. They now have a computer called the Dressel cone chip, which has 72 qubits, 72 quantum bits, which is quite a few. You can do a lot with 72 qubits. IBM is racing Google, and they've been sort of leapfrogging each other. The current IBM record is 50 qubits, and I expect them to keep leapfrogging each other, going back and forth about who's dominant in the quantum realm. But we also have other startups, small startups like Rigetti Computing, which has 19 qubits. And they're a spin-off of the academic sector, mostly coming from Yale, and they came out of nowhere, and now they're starting to compete with Google and IBM, which is an interesting turn of events. And of course, there's the academic sector, which is still actively researching this stuff. UC Berkeley, who I'm particularly involved with at the moment, they have 10 qubits. We expect to have 100 by the end of next year. No problem in the academic world. So it's taking off. It's taking off very, very rapidly. But these numbers don't tell the complete story. So I want to give you a more full background on exactly where we are right now and how far we have to get before all these benefits that I just talked about come into play. So first, let me give an overview of what are these technologies. So the first technology is trapped ions. This sort of led the way. It was developed mostly by people at NIST and also at University of Maryland and quite a few other groups. This is a very natural choice for building a quantum computer because atoms are quantum mechanical and atoms are identical. And so if you have atoms and you can trap them and you can manipulate them, then you can exploit their quantum mechanical nature quite directly. And that's in fact what they do. Is they take atoms, they ionize them, so that they can trap them using laser beams. And in fact, what you see here, I don't know whether you can actually resolve it on the screen. There's a tiny little dot hovering in between these two magnets here. So this is a big magnetic confinement of this ion here. And this is the whole idea, is you trap the ion, and then you can shine lasers on it, and then manipulate it and do all of these gates that I was talking about, just with laser beams. Now the actual qubit in these cases are the hyperfine levels, ground state hyperfine levels of the ion. All that means is that when you have a magnetic field, then your ground state of your ion splits in energy a little bit, and then you can distinguish those two energy levels, and those behave like your bit states 0 and 1. And because they're quantum mechanical, you can get superpositions of those zeros and ones. So then what you do is you trap many of these ions in a row, then you can entangle them by having them interact with each other, then you can get everything I just talked about as big superpositioned, entangled superpositions of all of these bit states of the hyperfine levels of all of these ions in a row. It's very complicated, takes a huge amount of hardware, but it works, and it works quite well. The second technology, which is superconducting qubits, has come on the scene much more recently. I would say that this brand of technology is now about 10 years old. This circuit that I drew here, which is called the transmon, was demonstrated in 2008 and is still sort of the workhorse behind most of these superconducting circuitry. But the idea is that if you have a superconductor, so you take a metal, in this case just aluminum, and you cool it down toward absolute zero. So you get down to in the millikelvin range of temperature. Then aluminum becomes superconducting, which means all the resistance of the wire goes away. And because you have no resistance, and because you can reduce the thermal energy fluctuations in the sample down below the level of the quantum regime, then you can start resolving energy splitting within those metal wires themselves. And what that means is you can actually engineer something that is actually quite large. This circuit that you see here with the scanning electron microscope, this little junction here you see is 200 nanometers, which is actually huge on the atomic scale. 200 nanometers is big. But this little junction here acts like a nonlinear inductor and is connected to a bunch of capacitors, and we get effectively a nonlinear LC circuit, which means you get charge oscillating back and forth in this sample, which is on the micrometer scale. So we get charge oscillating on the micrometer scale, but because it's superconducting and cooled way, way, way down, it still behaves quantum mechanically. And that means that in these charge oscillations, I can resolve discrete energy levels. And I can identify and measure discrete energy levels. And those discrete energy levels are now exactly what we need to build a qubit. So I just take the ground state of these charge oscillations in this micrometer scale device as the 0 of my qubit, and I take the first excited state above that as the 1 of my qubit. And by using these first two excited states, I now have a qubit, which I can engineer on the micrometer scale. And what's nice about that is I can then engineer a chip, just like I normally think about building semiconducting chips. I can just use aluminum deposition and just build many, many of these circuits in a row and connect them with aluminum wires and manipulate everything electrically, just with electrical signals. And it turns out that because these energy spacing is at the microwave frequency, then if I send in voltage pulses that are AC signals at microwave frequency, I can now interact with the quantum nature of these circuits and manipulate them. And that's what people do. The benefit of this is that it's extremely fast. We can manipulate these circuits on the nanosecond scale, as opposed to the ions where I have to shine lasers and move things around and is much, much slower. So because of that, these superconducting circuits are taking off as an actual scalable technology that we can use. And what I'm showing you here is a few pictures. At UC Berkeley, this lower left is the 8-qubit chip that they just released, and here are successive zooms in on that. So what you see are just usual coax cables where you connect just microwave signals directly to it. That interfaces with this chip, and if you zoom in, then you see all this hardware that's on it. This has 8 qubits, so here's a qubit, there's a qubit, there's a qubit, etc. These qubits are connected with resonators, just microwave resonators, and lots of other stuff in order to control them, to measure them, etc., etc. But it's all there on the chip. And it works extremely well. And the technology is only getting better. So here's an 8-qubit chip, but like I mentioned, that's small potatoes compared to what is now on the market. So let me give you a visual tour of what the recent developments are. So starting with ion traps. So you see this Nature paper from about 2016, August. There's a big splash where people with ion traps were able to get 5 qubits. They got 5 ions in a row. And if you zoom in way deeply in here, you'll see that there are literally 5 ions hovering next to each other in a row that they can manipulate with laser beams. And here's an artist's depiction of what that's like, with all these quantum probability waves flying everywhere, these lasers coming in, dancing ions, blah, blah, blah. Here's what it actually looks like. And this is Chris Monroe. He's at University of Maryland. He's one of the main drivers of the ion trap movement. And you see these optical tables with just reams and reams and reams of hardware to control these lasers. This is a small fraction of what's required to run these systems in his lab currently. It's actually a full room of all these laser equipment. And what they showed recently, this year, which is only, 2 years after this big 5-qubit chip, was this. Every row of this is actually what they did, and he managed to trap 53 in a row. So now we have 53 qubits all in a row, and he can measure all of them independently. And so what you're seeing here is each of these rows is a different measurement run, just seeing whether these qubits are on or off. If it's dark, it's 0. If it's bright, it's a 1. So when you measure it, you just get your classical bit string. But he's able to entangle and manipulate all 53 of these in a row. So that's pretty impressive. But of course, hovering things in a laser trap is a little bit hard to scale. So people have interesting ideas for how to extend these ion trap technology, which is to build a chip, much like the superconducting chip, except instead of having the chip itself behave quantum mechanically, what you do is you hover these ions above the chip a little bit. You just use the intrinsic electromagnetic field from the wires on the chip in order to levitate ions above the surface of the chip, and those will be your qubits. And by levitating them above the surface of the chip, you can move them around now just with electrical pulses. And if you move them around, they'll entangle each other, they can be measured, and then you can use laser beams parallel to the surface of the chip in order to read out what these ions are. And let me show you a little video here, or at least a fraction of this video, of their design idea, which is you levitate an ion, like this here, above some chip, and you literally move it around the chip mechanically using electrical signals. Bring it close to another ion, then you can entangle them, interact them, and then perform your computations this way. And the idea is you can have many such ions on some plaquette of chip, like here. And what you'll see is that you shuttle them around, you take them to detection zones, you shoot it with a laser in order to read out whether it's a 0 or a 1. You get this big dramatic laser beam here measuring your qubit, and blah, blah, blah. But of course, in order to do something useful, you have to have many, many of these going on simultaneously in parallel. And so they're envisioning scaling this up by having this sort of dance of ions traveling all over this chip in plaquettes that they can engineer, which are super cooled and all sorts of stuff. Get liquid nitrogen cooling, electric things, and you put all these plaquettes like tiles in a row. And you connect them up such that they're actually well aligned, then you can have ions travel across the barrier between chips and really just travel around this landscape, interacting with each other, blah, blah, blah. And now what they've estimated is with this kind of design, if you wanted to run Shor's algorithm and do something interesting like factor a large integer, you can do it with this technique, but it would take about a football field's worth of these tiles of ions in order to do it. You can imagine an extremely large area, and technically it would work if you could get it all working in parallel simultaneously. In any case, it's a fun little video which they made. Just a matter of engineering. But it's a question, is that practical? And my personal opinion is that if you're mechanically moving around ions, that's extremely slow. And I don't think that the speed of the operations you're going to get will be scalable favorably in order to get something like Shor's algorithm to work. So I think it's technically possible, but you're actually not going to get the performance you need just because physically moving ions around is too slow. Which is why I kind of like this superconducting sector. I think it's promising for scalability. And this is the latest, greatest state-of-the-art you're looking at here by the Google team, which is called the bristle cone chip. What you're looking at in this solid gold chandelier is actually the inside of what's called a dilution refrigerator. So they put a big canister around this and then cool it down to millikelvin temperatures. In fact, the chip lies very close to the bottom here of this chandelier, and you get cooled progressively in layers. So this is down to hundreds of Kelvin, then tens of Kelvin, then single-digit Kelvin, then millikelvin as you go further and further down. And at the bottom, you stick a chip, which is just this little thing here, and that's where your qubits are. All of these coaxial connections here are simply to get the signals in and out in order to talk to your qubits electrically. But the benefit of this kind of technology is that now since you're using electronics, the speed at which you can do things is now at the nanosecond regime. It's much, much faster, orders of magnitude faster than shuttling around ions, which means that your operations will be fast enough to do something interesting. This bristle cone chip here was released earlier this year in March, has 72 qubits. But shortly before that, IBM released this one, which is very similar looking, with 50 qubits as a prototype for their IBM Q project. And IBM Q is actually consisting of 5 international sites, one of which is in Japan, one of which is in the US, et cetera, et cetera. And each of these 5 sites will have some big chip that they'll keep upgrading periodically. And they've already put one of these chips on the cloud. So if you go Google IBM Quantum Experience, you can find a cloud version, cloud access to one of these chips and use it right now, which is exciting. And they plan to keep extending this prototype. They've also developed software. Like you see, Jake Mbeda here is prototyping on an iPad some of their interface for programming one of these quantum computers. Nice drag and drop interface for how to use these gates in these reversible ways. And you can program it in this nice way and then run your computation directly on their chip. And Google will put their chip on the cloud relatively soon. They've had plans for this, but IBM beat them to the punch. Rigetti Computing is a spin-off, like I mentioned earlier. They're a small company, but they're growing extremely rapidly. They're hiring like crazy. They've expanded in the span of about 2 years from nothing to having a 19-qubit chip. And it's modest in comparison to the previous 2, but I expect that they will have a lot very, very quickly. And as I'll talk a bit in a second, they've also been pushing a huge effort towards software of how do you encode these things. Okay, so these pictures are great to see what is the state-of-the-art technology. But still, the elephant in the room is how many do we actually need to do something interesting, something useful? Well, let's go back to Shor's algorithm, because that's sort of the gold standard. If we can get that to work, everybody gets really, really excited. And let's go big and use 2048-bit keys. This is ultra-secure RSA encryption. Well, ostensibly, Shor's algorithm needs 2n qubits to factor an n-bit integer. So already, that would put us in the sort of 4,000 qubit regime. That's pretty close to the regime we're already at. But there's a giant caveat to that. So it seems like it's only 2 orders of magnitude, which should be just a few years away. But in order to run this algorithm, qubits need to be absolutely perfect. And none of these laboratory qubits are even close to perfect. You have errors. And when you have a continuous range of degrees of freedom that you can maneuver in, any small error is catastrophic. So you have to be very, very, what's the word? Careful with your qubits. So there is a way to get around this problem, which is called quantum error correction. And this by itself is kind of a miracle that it works at all. So I'll walk you through how this works very, very briefly. But the idea is that since quantum coherence is so sensitive, you need to encode the information redundantly. Just like you encode information redundantly to protect against classical bit errors, it's the same kind of idea, but sort of on steroids. But what that means is that you can't use these just physical qubits in the laboratory directly. You have to sort of redundantly encode the information you want using many of these physical qubits in order to get an effective logical qubit that's error protected. And then you use these logical error protected qubits to do your actual computation. And that puts an enormous overhead on your computation. So to give you an idea of how this error correction works, classically it's very simple. You take a 0, you duplicate it. So if I have 3 zeros to encode a 0, then if one of them flips, I can use majority voting and tell, oh, it was a 0, and just flip that one bit back. Extremely simple. Turns out for qubits, you can almost do this exactly, but there's a caveat. You just take your 0 and 1, you have a superposition between them, and you can just duplicate your bits now and get a superposition between the duplicates. No problem. Works just like classical error correction, but you can't look at the bits anymore. Because if you tried to look at, say, is this bit actually a 0, then it would collapse the superposition, and you'd get, oh, only these 0, 0, 0 state, and you'd lose all the information, which are these alpha and beta that you're trying to encode in your state. But there's a way around this, which is to not look at the bits. Instead, you look at the parities of the bits, which means you ask, are these first 2 bits the same, or are they different? And what's interesting here is that if I look at this encoding, 0, 0 is the same, and 1, 1 is the same. So if I get an answer of yes, those first 2 bits are the same, nothing changes about this state. It's valid for the entire superposition, so the information is preserved. And I get that useful information, which is that the first 2 bits are the same. I can do the same thing with the second 2 bits, and then I will know if a bit flips. Because if a bit flips, then the parity flips. And if I measure several parities, then I'm able to detect which of the bits flipped without causing any collapse of the superposition. It's just really fun. But the problem is, this is very nice, but it's not enough. Because again, there's a lot more room in these quantum bits than just flipping or not flipping. They can sort of travel all over spheres individually. But it turns out, and it's kind of a miracle this works, that if you redundantly encode several types of parity, sort of a parity in this direction and a parity in that direction on my sphere, and I measure them, then I can protect against every other possible error. And that's remarkable. You can think of this as if I want to label a point in 2D space, for example, it's sufficient to label an x-coordinate and a y-coordinate, and then I know where it is. It's the same kind of idea. So if I measure the parities this way and I measure the parities that way, I can actually protect any point in this plane. And it turns out that that's sufficient. You can protect against all errors by doing this multiple parity measurement like this. So, in order to scale this up, some very, very clever people, namely Austin Fowler, and who's now working with the Google team, found a way to do this and scale it up for a large number of qubits. And the details are hairy, so I won't walk you through the full details. But the idea is kind of simple, which is that I create lattices of qubits, two-dimensional lattices, where each of the qubits interacts with its nearest neighbors, and this is really nice. And then I have interspersed sublattices, where one sublattice with the white circles here is a data lattice. Then I have 2 other sublattices, these yellow lattices and these green lattices, which are 2 types of parities that I measure. And so they measure the parities of all the qubits around them in one direction and the other direction, and you just alternate these parity measurements. And by getting collectively all of this parity data over the entire lattice, you can protect against other errors that will happen that will destroy your quantum information. And what you end up doing is encoding your actual information you want across a whole area of this lattice. And the beautiful thing with this code is that the larger the area, the more protection you get. And so if you start with reasonably good qubits, like 10 to the minus 3 error, for example, then you scale up the area, you can get your net error for your logical encoded qubit down to, say, 10 to the minus 15, 10 to the minus 20. And then you're talking, you can actually do computations when you get to error that low. But it takes relatively large areas of this kind of lattice in order to get your errors from a physical regime of error, like 10 to the minus 3, down to a sufficiently robust error, like 10 to the minus 20. Roughly speaking, Shor's algorithm will need 10 to the minus 20 tolerance and error. If your hardware is about 10 to the minus 3, then it takes about 10,000 physical qubits to encode one logical qubit that has an error that's down to 10 to the minus 20. So 10,000 per one qubit. So that puts a damper on our enthusiasm a little bit. 10,000 is a lot. But it's a little worse than that. So here's your 10,000 per logical qubit times 2 n logical qubits to factor an n-bit string. But it turns out you also need about a factor 15 overhead just for algorithmic details in Shor's algorithm. What you're actually doing is distillation of a bunch of useful ancilla states, which I won't get into. But you need to do all of this distillation in parallel with the actual computation fast enough so that you can do the computation. That leads to just an overhead in the number of bits you need in order to do all the parallelization in the algorithm itself. But you can treat that as a factor of 15. What you end up with is that if you want to factor a 2048-bit string, you're actually going to need about 1 billion qubits. Once we hit 1 billion, then we have a prescription and we know what to do. We can run the algorithm. So that gives us sort of the space axis of my computer. But there's also a time axis. How long does it take to run this algorithm? And it turns out that for superconducting qubits, we're in good shape. To run this factorization algorithm takes about 3 times 10 to the 11th of these Toffoli gates I mentioned. Each of those gates takes about 100 nanoseconds on a superconducting qubit. And so if you put that together, that means you can factor the number in about 27 hours. So factor 1, 2048-bit number, 27 hours. And if that sounds like a long time, you should compare that to what a classical desktop computer can do using the current best classical algorithm, the number sieve. It would take 6.4 quadrillion years currently to factor that same number with our best algorithm. Quadrillion years is well beyond the length of the universe right now, the duration of the universe. Well beyond. So it goes from absolutely impossible to take about a day. And that's why people are excited. But we have to get up to the scale of 1 billion before this is really possible. Good. So how long will that take? How long till we get to 1 billion? Well, if we plot a few data points about how this has been growing, it turns out that we've been growing exponentially. We're seeing Moore's law, the quantum version, the quantum Moore's law. The number of qubits as a function of time is growing exponentially. Here we see in 2016, February, Rigetti Computing beat everybody to the punch, this little startup company, and had 3 qubits working. And then IBM came with 5 qubits, then Google with 9, then IBM with 20, then IBM with 50, and then Google just trumped them with 72. And this is following almost exactly an exponential curve in time. So if I'm extremely optimistic and I say this exponential scaling will continue, just like Moore's law seems to have continued beyond all reason for as long as it has, then we would expect this exponential scaling to bring us to 1 billion in about 10 to 15 years, which actually is not that far away. There's a whole lot that has to go right in order for the scaling to continue. There's a whole lot of technical problems. How do you get the wiring into these chips? How do you get a refrigerator large enough to cool 1 billion qubits? These are engineering problems. They may have solutions. They may give us a hard stop at one point. We won't know till we get there. But if we just say, based on history, everybody's ability to predict the future has failed, and Moore's law keeps growing, well, we can do the same thing here and say, let's be super optimistic that people are clever, and we'll keep going exponentially. 10 to 15 years, we'll have a computer that's really significant. But then the question is, what do we do in the meantime? 10 to 15 years is not that long, but it's still kind of awkwardly long. Can we do something interesting before we get to Shor's algorithm scale? And it turns out the answer is yes, and there's a lot of active research right now to figure out what do we do in the near term. Once we get beyond what a classical computer can do, which actually we're right about there, everything in this left part here is classically simulatable. Once we cross this barrier here and get to around 100 qubits, I mean, we're basically right there, then we can no longer classically simulate it anymore, which means a computer can technically do things that we could not do with a classical computer. We just need to find what those things are. So there's going to be some applications here. And Google has outlined this research direction, where they want to really zero in on the near-term applications while still working progressively toward this full error-corrected landscape, the full surface code running in order to get Shor's algorithm eventually. So what are some of the near-term applications? One of them is quantum simulation. And this is a very easy idea to understand. It was proposed by Richard Feynman in 1985, which is that if you have a quantum system, you can simulate other quantum systems much more easily with that than you can with a classical computer. And this turns out to be true, that you can. And quantum chemistry is one of the fields that will benefit from this. And quantum chemistry dictates things like fertilizer analysis, blah, blah, blah. Making new drugs, making new fertilizers. All of this requires simulating how molecules fold, how molecules interact with each other to great levels of detail. And for large molecules, we simply can't do it with any of our superclusters. It's beyond the reach of our current superclusters entirely. But a quantum computer can start doing that, and in fact, we've estimated with the latest and greatest algorithms that are being developed that about 100 physical qubits is enough to really start approximating solutions to really interesting problems. And if we get up to 100 logical qubits, so again, another factor of thousands over the physical qubits, then we can start getting exact solutions, and we know how to do it. So this will be exciting in the near term. And in fact, here's experimental data that shows that we're already starting to do this. This is a 3-qubit chip that's computing the bond energy of a hydrogen molecule, an H2 molecule. And it computes the correct minimum energy, which sets the bond length between the hydrogen molecule, using a quantum algorithm running on a quantum computer. And these red dots are the actual data. The black curve is the exact solution, which we can compute classically, but we see we get something viable out in the quantum computer already. And the point is that if we scale this up to larger molecules, suddenly we won't be able to do it classically. We will be able to do it quantum mechanically. Okay, so I'll close with a few notes. One is that you can program a quantum computer now. I'll emphasize this again. IBM Quantum Experience, it's a cloud computer, you can go play with it. I encourage you to do this. They have 16 qubits on the web for free. If you're willing to pay lots of money, you can get more qubits than that, and that will only go up over time. The other thing that's really exciting is that people are starting to think about how do we program these computers? We have them here. How do we write code that actually uses them in some way? So Microsoft is in on this. They've been developing a full stack software interface called the Quantum Dev Kit. They've developed a new language called Q#, which is based off of C#. Here's some example code here. IBM's been doing this because they're developing the actual hardware. They call it a QIS kit. They have the whole development kit library with the whole sequence of compilers, circuit generations, executions, conversions to actual pulses that you send down your chip, etc. And it's based in Python. So here's some Python code that you have here. Rigetti Computing has also been doing this very heavily. For such a small startup company, what they've output is really impressive. They've just output a scheme called Forest, which has the full quantum to classical processor, hybrid algorithms together. They've developed an assembler language called Quill that's general for a quantum gate-based architecture, and a Python interface over Quill called PyQuil, which is shown here, of just how to program a circuit very quickly. And of course, people at, say, Google say, I don't want these corporate solutions. I want something open source that anyone can develop and use. And we have some open source project called Project Q that's doing this right now. And they are also using Python to do the full end-to-end software stack. And they're thinking about this quite seriously. So if you're interested in just getting into the nitty-gritties about how do you get from a software developer down to a quantum computer, that's what they're worried about here. And there's a lot of ongoing research there. So I'll close, because we're sort of running low on time, that quantum computing is already here, mostly. The rest is engineering details about how to improve it. But it's only a matter of time, I will say, before a quantum computer accomplishes a task that is currently impossible on any quantum computer. It's only a matter of time. I'm not sure what it will be, but it will happen. So with that, I will say thank you for listening. I'm happy to take questions.
Thank you, Dr. Dressel. Traditionally, our first question comes from Windsor, but Don already kind of asked it for him, which is the head count of the IEEE members. So, we have a question in the back.
Yes. What is your view on D-Wave and quantum artificial intelligence? Where do you see that going?
Yeah, you'll notice I carefully left out D-Wave from this entire talk. The reason is that D-Wave came on the scene saying, we have a quantum computer, look at us, we're this great company with quantum computer. But in fact what they had was what's called a quantum annealer, which works entirely differently than this gate-based architecture. It's unclear right now whether D-Wave can actually have any advantage over a classical annealer. And this has been a fun side detour because the Google team has a D-Wave system in parallel with what they're developing here. And they're trying to push it to its limits and say, can this really work and give us an advantage like we believe this universal gate-based quantum computation can? And they keep getting sort of ambivalent results. They released a paper that said, here, on this D-Wave machine, we've gotten 10 to the 8th factor improvement over the best classical annealing algorithm for this problem. And then people came out a few weeks later and said, oh, well, we tweaked our classical algorithm. We put quantum tunneling in there directly in the classical algorithm, and now we beat the D-Wave machine. So they've been going back and forth as this development of this annealing, which is a whole lot of fun. But I didn't talk about it because it's sort of a parallel trajectory where we might get quantum advantage in annealing, but it's a little unclear whether we will and what the future layout is for that.
And the second part is, when do you see quantum artificial intelligence come? Where do you see that in the next few years?
You mean something like quantum machine learning?
No, beyond machine learning.
Beyond machine learning. So I'm not even sure what quantum artificial intelligence would imply. I do know that people are thinking carefully about quantum machine learning and saying, if we take classical machine learning algorithms and make them quantum, do we get any advantage? Do we get speed-ups? The answer is still not conclusive, I would say. And there's also some effort going into, can we develop new machine learning techniques using a quantum processor that have no classical predecessor? And there's active research there, but still no conclusions. The last thing I'll mention on that topic is that the reason Google is so interested in a quantum computer is precisely because of machine learning, but in the opposite way. They want to take a quantum computer and train a classical deep neural network faster. And even if they get a constant factor improvement over a classical computer, just a factor of 5, that's worth it to Google because they work at such a large scale that factor of 5 is $1 billion improvement. If they can get better than the constant factor, they'll be even happier. But that's the main reason they're interested.
Here?
I mean, my general understanding of when you're measuring, one of these atoms is it's basically like taking a cannon and shooting a bowling ball out of it and having this flee in a sphere, and whether it splats on the wall or it doesn't is the 1 or the 0 bit. And so it seems like the reason why the measurement is so off is, the error correction is there is because of the measurement. And I guess, are they exploring any other solutions besides using light or anything else that could be, I don't know what is possible of potentially measuring these quantum systems that may make this 10 to the 9th of a billion more possible, I'd say, for I don't know. I guess that's kind of my question.
Yeah, so there's a few things to unpack there. The first is that your very violent analogy with the bowling ball and the mosquito isn't quite correct in practice. It turns out that when you measure a quantum system, it's exactly the same process as applying Bayes' rule to a probability. So if I learn some information, I have to update my probabilities with Bayes' rule, which causes a collapse of my probability toward a more definite outcome. This is actually the same mechanism that causes quantum state collapse. So it turns out that you can measure things not in such a violent way, but in a fairly gentle way as well. So I can get very small amounts of information, and that causes a small perturbation in my quantum state. In fact, this is one of my favorite areas of research. And moreover, say taking these superconducting qubits is a good example. The only way they can get information out about the qubits is by shining a microwave into the system, getting a microwave out, and then trying to find how the phase shifts in that microwave. And it turns out that you cannot do this as a projective or definite 0 or 1 instantly. You get small amounts of information per unit time about the phase of this microwave, which means that you're actually causing what's called a progressive collapse by taking small amounts of information over a duration of time, which means the collapse actually takes time, and it follows a random walk in order to do that. Which is a lot of fun, just conceptually and foundationally. So that's the first thing. The second thing to unpack is you mentioned, oh, well, all of these errors happen because of the measurement. That's actually not quite true, that most of the errors happen because of the environment of the chip. If I have thermal fluctuations in the chip, I have vibrations in the chip, I have all this other stuff around that's not storing my quantum information. Any amount of interaction there causes information to leak out to the environment, and that causes a degradation of my quantum information. Those sorts of errors are what the error correction is mostly protecting against. And so, of course, the better you can isolate your quantum system until you want to look at it or until you want to control it, then the less information leaks out and the less error correction we have to do. And there are working extremely hard to minimize all those sources as much as possible.
Behind down here, you had before.
Hi, my question is that the software examples that you show describe basically sequential languages, whereas this is a fundamentally parallel system. I am a hardware designer. We use a hardware description language, which is fundamentally parallel in order to design application-specific integrated circuits. Whereas what you have described is basically a general purpose computer, which is more or less running a sequential program. And I'm just wondering if there is a mechanism by which the promise of quantum computing can be brought closer to reality by recognizing that we can make maybe a special purpose Shor's algorithm only chip by describing it in a language which is fundamentally parallel, just like Verilog or VHDL is for normal classical computers.
Yeah, this is a fantastic question. Most of what I've talked about here is talking about the circuit-based approach to quantum computing, or the gate-based approach, which, like you say, is based on sequential reversible classical gates. That's nice theoretically because it allows us a clear passage back to classical land, and so we can prove definite things about whether the computation is better or worse than classical computation. But you're right, it's not fundamentally quantum. If we start thinking in a fundamentally quantum way, maybe we won't think about gates at all. We could do something completely different. That's still on the table. Maybe that is a better way to go. It's a little bit unclear right now what that would look like because we have no concept for it. In some sense, the annealing work, like by D-Wave and others, is kind of pushing in this direction. If we take a network and just wire a whole bunch of stuff together and it all just fundamentally works in this parallel way, do we get something that's better immediately that we can't reason about so easily? And the answer may be yes, but the jury's still out on that. The other thing is that for these classical algorithms, some of these things can be parallelized. When I have many, many qubits, you can just parallelize lots of operations, of course. And these, like Python is not the best kind of language for that, but Liquid, which I kind of like, developed by Microsoft, is based on Haskell, which is based on F#, which is based on Haskell. And the idea is to have more declarative, functional way of looking at it so that it figures out how to parallelize and compile everything just as a declarative system. So I kind of like, people are pushing in that direction a little bit, but of course programmers historically have had a really hard time understanding declarative languages as well as imperative ones. So there's some inertia in the programmer landscape there.
So hardware designers have a chance because they already think in a relatively
parallel now.
Absolutely, and if you look at these circuits, they're pretty much wires. So hardware people have a very good chance, I would say.
Use your best guess, let's see, how long, how many years from now, we can have quantum computer like today's desktop size.
You mean a quantum computer in the home?
Well, that's the home, but like a room, like regular office environment.
It's a hard guess because there's a famous quote, I think, from like the early, mid-70s, that, oh, nobody would ever want a computer in their household. This is completely crazy. And now we have them in our pocket, and so they were clearly wrong. So it's a little hard to anticipate what will happen. What I can say is I've only talked about the two dominant technologies, ion traps and superconductors. Superconductors have the disadvantage that you need a giant refrigerator to hold them in. And it's a little hard to expect that people would want to have a dilution refrigerator in their home. That's great for the cloud because you can have a whole server somewhere in the cloud that does all this hardware maintenance for you and you just log in remotely. But there are new technologies coming out that are based on semiconductors at room temperature. And quite remarkably, there's been some progress there in recent years of getting qubits to work at room temperature. And if that trend continues, then it's quite possible that there will be some semiconducting technology in the next 5 to 10 years that starts competing with these other dominant technologies. And that technology would have the capability of maybe going to someone's home in a much more straightforward manner. So I won't guess a time scale, but I'd say within 10 years, roughly speaking, we'll be able to say much more clearly, will you have mobile quantum technology or not? Right now, I'd say the possibility is vaguely there, but it's too early to tell.
Don, you have a question?
Yes, eons here about a question about the error distribution. We know what the error distribution looks like, or can you point me to a paper that describes the error distribution of the algorithms, not of the hardware that it's built in? Like you said, most of the error comes from the environment that the device is living in. But what about the errors that occur native to the quantum computing algorithm or technology itself?
Yeah, I think the best way I can answer this is that you're talking about what they call fault tolerance in the quantum computing community, which is that if you have an error that happens somewhere in an algorithm, then it can propagate through the algorithm and cause other errors. The fundamental error tends to happen in hardware, just like it does in normal computing hardware. Bit flips here, you get an erasure there, a cosmic ray comes in and screws up your computation, that kind of stuff. So the fundamental errors are all at the hardware level, but you do get errors that propagate through the algorithm as well.
I mean, the quote wave collapse, unquote.
Mm-hmm.
You have, you're sampling, you have this state of this machine, but you have no idea what it is until you measure it, and then you only get one of the states, right? So what is the error distribution in that domain?
This is all hardware errors again, because you actually will know what the state is if your machine is operating well, because you knew what it was to start with, you're keeping track of all the operations that are done on it, so you actually do have a pretty good idea of what it is even before you measure it. When you measure it, you get definite outputs, like you say, that are randomly chosen. And there is some readout error, like if when you measure it, you might accidentally get the wrong bit. Like it actually collapsed to this, but your device reports the opposite one. This is one of the types of errors. But again, this is all dependent on the specific hardware. And this is a very delicate topic to talk about because each hardware has its own completely different classes of errors that can happen in the hardware. And you'll get certain errors are more common here, certain other errors are more common there. And the errors of the physical devices don't necessarily map cleanly to the circuit model. Like they work in a space that's very different than this abstract circuit model. To give you an example of this, take a transmon. This is the qubit that's most used in the superconducting realm. The qubit is the lowest two energy levels of what ends up being an anharmonic potential well. But that anharmonic potential well has 5 to 7 levels in it. And so you can actually go outside of your qubit space into something that's not even defined as part of your quantum computer. It's just some other part of your physical space, and then stuff can happen there, and then it can backpropagate into your quantum computing subspace and cause problems. And so minimizing all these extra kinds of errors is extremely challenging and very hardware specific because of how you're implementing the qubit in that particular hardware. Does that answer your question?
Yeah.
I'll follow up afterward.
I'd like to go back to the error correction piece where you got up to a number like 1 billion qubits. Is there like a compromise where, say for Shor's algorithm, where you're going to end up with a couple of factors and then you're going to be able to decrypt? Could you not tolerate some level of error, do it 1,000 times, but then test the output by seeing whether it decrypts accurately or not?
Absolutely.
Or maybe cut the time that you, instead of 15 years, do it in 5 years, maybe.
Yeah, absolutely. You can think of hybrid algorithms where you sort of trial, get a bit more information, do another trial, get a bit more information. And even if you have noisy circuitry, then doing that kind of random samplings, so to speak, would have a positive effect. You'd be able to do something with that. I'm not sure I've seen any analysis of what it would take for such a hybrid sort of trial and error algorithm like that, and I'm not sure what the thresholds are. But I do know that, say, with the surface code for error correction, one of the nice features about it is that there's a fairly low threshold of how bad your errors have to be before you can start amplifying them or amplifying the fidelity and just decreasing the effective error. So based on that, I would suspect that we're already almost at the scale where we can start doing some of the surface code stuff, get the errors low enough effectively to do some of these trials, like you're saying, and see how well it works. I'd say you're right, that maybe in 5 years we'll be able to do something, maybe not at the 2,000 bit factoring level, but maybe a couple hundred bits are within reach by then. But we'll see. People are working on this pretty hard.
So you say perhaps in 15 years, most cryptography should be breakable. You get through and reverse the error.
Yes.
Optimistically, if all the scaling that I just laid out holds, which is a big if,
dramatic. 15 years, that would be very dramatic.
it would be dramatic.
Any research on cryptography that's
Yes.
quantum bits?
Yes.
Yes, this is a very active field of research right now because of the quantum threat looming on the horizon. And we actually know of some encryption algorithms already that seem to be immune to the speed up provided by the quantum computer. But the problem is that the overhead of using these encryption technologies is sufficiently high. People are not very excited to move to them in any short amount of time. The other problem is that RSA and so forth has now become so embedded in a lot of the software that it's actually hard to get out and replace it with something else. It's a huge just software refactoring job that is going to take huge numbers of man hours to complete. So there's absolutely an enormous amount of computation research that's being catalyzed by this looming quantum threat, and people are taking it pretty seriously, especially in the government sectors, because you can imagine state secrets you do not want accidentally being broken into within 10 years.
This is a real Y2K problem.
It's a real Q2K problem, yeah. Q million, billion, yeah.
I'm hesitant to bring this to a close, but we are kind of running out of time. I saw one hand in the back. Let this be the last question, and Dr. Dressel will be able to hang around for a bit and answer more questions afterwards.
Okay, are you aware of any government secretive, or not, there's efforts that are non-public? Or
I cannot confirm nor deny. I will say that there is an awful lot of funding coming toward quantum computing from government funding agencies, and leave it at that.
All right, good place. I'd like to present you with this certificate of appreciation on behalf of the ACM and their membership. I'm sure this will make all the difference in your application for professor.
Thank you.